So problem 7 here is the first one it gives us, where it now tells us that we've got a system not at equilibrium. So the flask initially contains 5 atmospheres of each gas. And so you might immediately think, oh, I got to do an ice table. Not yet. Those are coming. This is one where you simply need to answer the question, which way will the equilibrium go if we start out at these pressures? So we have to calculate the Q. And remember, the Q is the concentrations at the time where we're making the calculation. So in this case, it tells us there are 5 atmospheres on top and 5 atmospheres on the bottom. So our Q is 1. It must equal 3.4. So the only way it's going to happen is if this gets larger, and it gets larger by making more products. So it must shift to the right. So our answer will be shifting to the right. Now in problem 8, again, you're going to have to carefully read these questions. This one says, okay, we've got a 3-liter flask, and it tells us how many moles of 2 of the 3 parts of the system are at, and it is at equilibrium. So this is a matter of not doing an ice table, but just plugging in the concentrations and solving for the one equilibrium concentration we don't know. So I've written that out here, and that's where we're starting. And so we just have to do a little rearrangement. So we're going to multiply both sides by O2 concentration. And then we're going to divide both sides by this 1.4 times 10 to the 2. So it's 1.4 times 10 to the 2. That allows us to cross that out, and it solves for our O2 concentration. And now the trick here is that this is going to give us a concentration of O2. Now this is a little tricky, right? Because we've got to do some manipulations here before we get to our answer. So we've got to we're going to solve for this is O2 squared there, by the way. So we're going to do all this arithmetic, and that's going to give us O2 concentration squared. So we're going to have to take the square root of that. And when so that value was that I got was 3.81 times 10 to the minus third. That's O squared, and so I got to take the square root of that. And so my O2 concentration, once I take the square root, comes out to be 6.17 times 10 to the minus 2. Now that's moles per liter. It's in molarity units. And this asks for the number of moles, so we're remembering we're in 3.0 liters to cancel those liters, and that comes up with this answer that's 1.85. Okay, here is problem 9, and we encounter now our first ice calculation, because what does this do? It gives us an equilibrium constant, and it tells us our initial concentration of O2. So I've written out this is the equilibrium expression, and our ice table then is just going to be entries for O2, and then we're going to solve for the SO2, the X, right? So our initial concentration here is 2.9 of O2, and this is 0. And so our change is going to go to the right, so that's going to be minus X, and that's going to be plus X. And then this is going to be 2.9 minus X, and this is going to be X. Now, remember, this is asking us for the equilibrium concentration of O2. So we're going to solve now for X, and then we've got to subtract 2.9 minus that X to get our O2 equilibrium concentration. So don't forget to do that, but this is just going to be a matter of our 1.5, well, our value here is going to be, that's our equilibrium constant, and that's going to be equal to our X over 2.9 minus X. So I do my rearranging, and I am not going to be able to finish this on this. So I've just got a few seconds here, and I've done the rest of the algebra. Don't forget, you've got to take that 1.75, subtract it from 2.9.